Hello, people. Hope you guys are doing well. And I'm going to start with the new material here, where we're going to be looking at phasor circuits effectively. And as we do this, I'm going to try to, physically give you reasonings for why we have to go this route. So let's go look at this here. So I'm going to go share my screen with you and start doing it. So what we see here is that we're now going to be looking at sinusoidal / AC steady state analysis. And there's a couple of things that we want to say. First thing that we want to talk about is that we want to talk about sinusoidal sources and where we're going to go with them. So when I think about sinusoidal sources here, we want to look at what do I mean by a circuit here. So if I have a source, so you could imagine that if I have some circuit that's AC, that means that the voltage source here is going to have some maximum amplitude. And let's say that it's cosine omega of t. It could be cosine. And then I have some circuit here. Now, one of the things that we've seen here is that if I have a circuit that does this here, we know that if I solve this circuit using differential equations, so if I solve using differential equations, what we find here is that I have a natural response and I have a forced response. And what we're going to see here is that we know that in some shape or form, this natural response has an exponential term that starts to kill this thing off. And then our solution should then have some amplitude of either cosine omega t and A2 sine omega t. And what we find here is that after 5 tau, the natural response is gone. That means I expect that the complete response should be exactly the same as the forced response. And what we're going to see here is that the way we're going to write it is that we're going to have some maximum amplitude, and we'll write it in such a way that it's omega t plus some phase constant. So what we're seeing here is that I'm going to get a function that has no natural response. So the only relevant thing here is the forced response. Clearly, these functions are periodic. And what do I mean by periodic? That means that if I look at some function at time t, at some time t plus capital T, I get the exact same function. This tells me then that in our case, we're then going to have omega t plus theta. Actually, let's not consider a phase for right now. So then that means here that this function should be exactly the same as t plus the period later on, which then tells you that I get omega t plus omega period like this. So right away, just by looking at this term right here, we see that implies that it must be periodic. So this term here tells us that that omega times t must be a function of 2 pi, which then tells us that therefore omega is 2 pi over the period, or I can write this as 2 pi times the frequency. So we're always going to know the shape of the forcing response because we know that it's periodic. So what we want to do here is that this is what we want to do. We want to write solutions that are, of course, 1, periodic, and 2, only depend. They only depend on the amplitude and the phase. So the amplitude in this case, I'll just call it x max, and the phase. And what I know about the phase here is that it's theta here. So we want to write a solution that are periodic. So we know that it's got to be some function of sine. And then 2, when we look at the solution, there's 2 terms. There's the amplitude, and then there's the phase angle. That's the arbitrary. And what you're going to see here is that these solutions will take on phasor form. What does phasor form means? It means this here. It's a vector in the complex plane. A phasor is a vector in the complex plane. So since we're talking about waves, then let's make a simple definition. Because these waves are going to be out of phase. We just talked about the phase angle theta. And here's how we define it here. If the current reaches its peak value before the voltage, one says that the current leads the voltage. It leads the voltage. In other words, I leads V. So to give you a sense of what do I mean by this here, okay, because that's something that's going to come up quite a bit here, is that I want to start off by looking at a simple example. So one example would be is that suppose we have 2 values. Suppose we have a current, let's say green. So I have a current I of t, which is 8 sine of 4t minus 1/3 pi amps. And then I have a voltage. I have a voltage of t, and in this case, this guy's going to be 6 sine of 4t plus, let's say, 1/6 pi volts. So what I'm going to do here is that I'm going to look at the phase difference. So between these 2 functions here, I'm going to look look at the phase difference. So if I look at this phase difference, I'm going to define this function as theta. So in this case, this means here that if I look at the difference between these two, look at the phase of the voltage. So I'm going to look at the phase of the voltage minus the phase of the current. Okay, so I'm going to run out of space here, so I'm going to move this. I'm going to move this over here. So how about if I do this? I'm going to come over here and copy this. So if I now just put this guy down here, here's what I'm going to see. So I now have a phase difference that I've defined here. So when I read this, this guy's going to be what? It's going to be 4t plus 1/6 pi. And then I have my current phase, which will be 4t minus 1/3 pi. And I'm going to subtract the difference here. And if I subtract the difference, I have a 1/6 plus 1/3. That should give me 1/2 pi. So in other words, the phase difference is this right here. So what does that tell me when I have a phase difference here? So if I look at this thing here, that pi, so if I look at this picture, what does it really say here? So if let me draw a nice good picture here. So let's say that this guy is this thing right here. That's where I'm going to set my 0 here. So this is theta equal to 0. So if I look at this guy, let's say that this is my axis. So it's not okay to compare current and voltage on the same graph because they have different units. So we're not really interested in trying to get sort of like the right amplitude because that doesn't make any sense. So I'm going to draw them the same value here. And this is what I want you to think about here. So what you're going to see when I do this here, you're going to see the following thing. You're going to find here is that when I look at the green phase for the thing, remember the minus sign means that it gets translated to the right, whereas the positive sign, you get translated to the left. So what I'm saying here is that the phase of the current of minus 1/3 pi implies that it shifts to the right. Whereas if I look at the phase of the voltage of plus 1/6 pi, it gets shifted to the left. So when I look at the peak of the wave, this is what I'm seeing here. So the peak of the wave tells me that the green is peaking after the curve. I mean, after the 0 mark. So how much did it peak by? Well, you could see that it's 1/3. So then that tells me that the phase difference from here to here, let me do a little bit better job. So if I look at this peak here, that tells me that the distance from here to here in this space here, that guy is 1/3 pi. Okay, and that's going to be the current I. Because of the phase of the voltage being to the left, that means then its peak is over here. So now if I look at this peak, you could see that this peak is then going to look something like this here. And so if I now look at the phase of this wave, what you're going to see here is that the distance from here to here, that is going to be 1/6 pi. So when I now look at the phase difference between the two waves, then the phase difference between these two peaks here is delta theta, which of course we just computed is 1/2 pi. So in this case, because the voltage V of t peaks before the current, we then say this, that the voltage leads the current. Okay, we now know that that has to be the case here.
You have a dentist appointment tomorrow at 2:45. Okay, left alone.
What we want to do here is that I now want to do something different here. I want to show you why we need to go into the phasor form. Okay, so let's go look at this here. Why do we have to do phasor form? And what I'm going to do here is that I'm going to do this by example to show you what I mean. So what we're going to do now is that we're going to transition from differential equations, which is in our case chapters 7 and 8, to phasor techniques. Which in our case is going to be chapter 9. So this is a pretty mathematical chapter. So let's see if we can do this right. So what we want to do here is that we want to start with force responses from chapters 7 and 8 and convert them into an amplitude and a phase constant. Okay, so we want to convert the solution into that form. So what you're going to find here is that I'm going to have to rewrite my solutions. So here we go. So here's what we're going to see. So we start with a or is it a, how was I calling this? A sinusoidal surface. A sinusoidal source. Sinusoidal source. Now there's lots of ways to actually do this, but the way we're going to do this here is we're going to assume here that we have a circuit where the voltage source is then going to be some amplitude times cosine omega t. So this is what our source is going to look like. And of course, now we have some load here. And so when I'm looking at this load, that's what we're really trying to solve. So if we look at this thing, here's what we find. So our goal is going to look something like this. We want to take chapter 7 and 8 solutions to this. That tells us that x of t will be the natural response plus the force response. And we already have discussed that this guy here is 0 because we're going to reach AC steady state. And then what we're going to do here is that we're going to rewrite this where I need a linear combinations of sine and cosine. So I can have two arbitrary constants, right? In this case, these two are my arbitrary constants. And what I'm going to do here is that I'm going to shift it to these. And the way I'm going to shift it here is that I'm going to call this A cosine of omega t minus some phase. Now note, I could have written that as a plus. And so what you're seeing in this case here is that you could see that the amplitude and theta are now our arbitrary constants. We're essentially passing the buck down. So what I'm going to do now is that to get the force response into this form, I'm going to have to employ a trick. Okay, so let me slide this up. Okay. To get the force response into this form, that is with A and theta as arbitrary constants, we will use a I don't know, a triangle trick, for a lack of a better word. And what we're going to do here is that this is what we're going to do. I'm going to write my solution where I still have B1 cosine omega t plus B2 sine omega t. So note, one of the things that I can do here is that I could multiply and divide by the same quantity. So look what I'm going to do here. So I'm going to take the magnitude of A B1 plus B2, and then I'm going to multiply it by the same thing. So then I'm going to get B1, B2 squared, and then this will be B1 cosine omega t. And then, of course, I get the exact same thing here, except I now have B2 instead. And this forms here beg that we're talking about some triangle. So now, using the triangle trick, you could see that these terms look like triangular terms. So if I look at this thing here, let's set up my triangle. So here's my triangle. And then I could then come in here and I could just say, okay, check this out. I'm going to make this B1, B2. Then this guy, of course, is then going to be B1 squared, B2 squared, square root. So now that I have this, you could then see here is that this implies here that I can choose, look at the B1. So B1 over the hypotenuse, which tells me that theta being the adjacent angle, then says that cosine of theta is then, of course, going to be B1 squared, B2 squared, square root, divided into B1. Or I can look at the opposite angle, as expected, and I can write this in terms of B2. And if I take the sine and cosine of these guys, the tangent, in other words, as we typically do here, then this guy should be B2 over B1. Exactly what we would expect from a triangle here. So what we want to do here is that to give you an example of what this does here, it looks something like this here. So what we want to do is we want to do the following thing. So if I look at this thing, let me make sure I get this right. Oh, there's one other thing I forgot to mention here. It says we will also need a a, a trig identity. And the trig identity that I want to use here is I can write cosine of theta cosine omega t plus sine of theta times sine of omega t is that this, of course, is cosine of omega t minus theta. So you could see that I'm really, really close to doing this thing here. So I now have this trig identity, and I now have a solution that looks like this here. So now let's go apply the solution. So if I look at this solution here, here's what I'm going to find. So as an example, check this out. Suppose we have this function. I have x of t. This is going to be minus 5 cosine of t plus 12 sine of t. Okay, if this is the case here, my job here is that I want to rewrite this thing. I want to rewrite this thing so this guy is going to be the form of a cosine omega t minus theta. So my job here is to do one of two things here. So we want to determine the amplitude, and we want to determine what the phase looks like. So our job here is to determine A and theta. Okay, so let's go do that. So here we go. So if we look at up here, this result here is that if I have a function that reads like what? B1 cosine omega t plus B2 sine omega t, how do I get my A? How do I get my theta? Well, I'm going to look at these relationships here. So the first thing that I'm going to see here is that B1 in this case, I mean, I guess it doesn't really matter how I'm going to choose these guys here, but I'm going to say that, hey, let's say B1 is minus 5. B2 is going to be 12. So this immediately tells us here that B1 squared plus B2 squared square root is then going to be minus 5 and 12 squared, and I'm going to get a value of 13. So the tangent of theta tells me that we're talking about B2 over B1. And if I plug these values in, I'm going to get that this is going to tell me that theta is the inverse of this, which will give me 12 divided by minus 5. And if I compute this, I'm going to get 167 degrees. Now, I got to be careful here because I squared this. Note that the angle is getting reflected. So what I have to do here is that I have to add 180 degrees. So if I do that, this gives me 113 degrees. So now that I've done that, you could see that I've now dealt with the square root term. I've now dealt with the angle. And so this tells me here is that these guys here tell me that I can write a function such that it looks like this. I have x of t. We started off as minus 5 cosine of t plus 12 sine of t. And now if I start to convert that into an amplitude and a phase, you could see here is that this guy should be the square root of b1 squared. So this is going to be 13. And then I'm going to get cosine of 5t minus 113. And how, oh gosh, I forgot to mention this here. Well, no, it is. It's right there. So now this is what that solution looks like. Once again, we took our arbitrary constants and we moved it right here. And we moved that guy right there. So these are our two arbitrary constants. So now that we've done that, what I want to go and do here is that I want to go in and just remind you that in summary, there's a way to move from solutions of one form into another. In other words, I can have a solution that looks like this. And then now I'm going to come in and I'm going a solution that looks like this. And I'm going to get cosine of omega t minus theta. Right? So this is from this solution here is essentially solution from chapters 8 and 9. And then this solution here is the transition to chapter 9. Okay, so now let's start moving towards starting to look at steady state AC. So here we go. Steady state AC response of a first order circuit. Okay. So what I want to do here is that I want to apply these techniques to a first order RL circuit here. So here we start. So remember, we're going to look at AC steady state. So for AC steady state, remember what I mean by that, that the natural response has died out. Okay, so now that I know that, I then have my circuit here. So I'm going to have some voltage source, and then I'm going to have a resistor, and I'm going to have an inductor. So this is L, this is R. And so what I want to do here is that I want to go in and I want to apply KVL to get the inductor current. And from that inductor current, I want to write it into an equation that has an amplitude and it has a phase constant. That's what our goal is right here. Okay. And it goes something like this here. So now we want to determine the IL response where we have the amplitude and phase combination as our solution. Okay, that's what we want to do. So now that I got that, and I know that a lot of you are not really experienced with looking at phasors. I mean, phasor circuits here. And phasor results from physics 4B. So what I'm going to do here is that I'm just going to tell you that this is what we're going to head for. What we're going to head for is that if you had done this in circuits, or if you had done this in physics 4A, what we're going to see here is that there's a summary. Okay, there's a summary that I want to do. If you have an AC circuit, what you're going to find here is that you're going to find two things. You're going to find here that we will find that the amplitude and phase are frequency dependent. That's a big deal. That is a radical difference from what you saw in chapters 7 and 8. Those amplitudes were constant. That is not true when you move towards a phasor technique. Now note, we have not used the phasor technique yet, because a phasor technique means that you're mapping a time-dependent solution into a frequency-dependent plane, the complex plane. So we're not there yet, but that's ultimately what we got to show. So what I'm going to show you here is that because of the amplitude and because of the phase being frequency dependent, if we use chapter 7 and 8 techniques, they just don't work for us. It will not work. So here we go. So what I'm going to do here is that I now want to put in some details into our circuit so that we could go in and start to look at that. So I'm going to tell you, this is messy. Okay, and there's a better way. That's why I'm doing this. I'm trying to transition you from chapter 7 and 8 thinking to chapter 9, because it's way more powerful. So here we go. So I got my circuit now. So what we want to do here is that we want to solve for the inductor current. And so here's my circuit. So I know that my source, I could either make all my sources cosine or I could make them sine. It doesn't really matter how we do them, but in this course, we're just going to assume that they're always cosine. It's a standard for many circuit textbooks. So here's my circuit. And of course, here's my R, and this is my L. And what am I solving for? I'm solving for this inductor current as a function of time. And we want to write it into the amplitude phase thing here. So how do we solve nice circuits like this? We use KVL. So what I'm going to do now is from here, I'm going to apply KVL. And if I apply KVL, you could see that the source clearly has to supply voltage to the resistor in the cap, or in the inductor, excuse me. So I'm going to say that I have VR plus VL should be equal to the source. So if I write out the details here, look what I'm going to write. This should tell me that, look at my inductor. My inductor should be L S hat I. And then I'm going to get R times IL. And then this guy is going to be some amplitude times cosine of omega t. So right away, I have my KL equation right here. KVL equation. Now that I got that, we know that the force response is, as we've been writing it in class, we'll say here that this will be B1 cosine omega t plus B2 sine of omega t. But I said that that way really sucks. So that means we want to go to something that reads an amplitude times a phase. That's our goal right there. So what we want to do here is that to try to convert that, what I'm going to have to do here is that I'm going to have to determine the constants B1 and B2. Okay, so the only way that I can do this, right? So the only way I can get to this, so if I look at this here, and I look at this here, I must know B1 and B2 to determine these two arbitrary constants. Okay, so let's go do that. So how am I going to get B1 and B2? The way we always do. We take the force response and we plug it into the differential equation. So to determine B1 and B2, we sub in the force response into our KVL equation. So here I go. Look at my equation. It's L, right? So look at that. So I'm going to get L. Then I got to take the derivative of what? This term. Plus R times our solution. Oops. And this guy, we're going to force it to have the form of Bm cosine of omega t. So now that I have that, what I'm going to do next here is that I'm going to go in and I'm going to set up my equations here. And what you're going to see here is that I'm going to have a combination of cosines and sine terms. And the only way that could be true here is that they're equal to each other here. So what I'm going to do here is that I have to collect cosine and sine terms. So let's collect cosine omega and sine omega terms together. So here we go. So here's our cosine omega term. So if I look at a cosine omega term, look at that. There's cosine. Ooh, no. I got to take the derivative of this thing. Damn. Okay. Let's see if we could do this. So let's stick with the cosine omega term here. I forgot about the derivative. So here I go. Look at the first term is going to be sine. Okay. So I'm going to say that the red is sine. This is sine. And then my cosine terms are going to be the green ones. Okay, that has to be the case. So let's take derivative of B2. If I take the derivative of B2, note that there's no sign change. So I'm going to get what? Omega times L times B2. So I'm going to get, so my first term is going to be, let me make sure, omega L B2 plus R B1. And then on the other side, I'm going to get VM. So again, these guys are my green terms. So now let's go look at the signs. So if I look at the sign, it's all the red terms. So the red terms got to give me a minus sign because it's the cosine. So it's got to be minus omega L. And then I'm going to get B1. And then the second term is then going to be R B1. No, I have a sign error already. That's a 2, right? Because we're looking at the red terms. And then, of course, this guy is 0. So what you're seeing here is that the only way this could be true here is that this gives me a 2 by 2 matrix, right? So this gives me a 2 by 2 matrix. So I have a 2 by 2 matrix solution. So if I do this, look what I'm going to do. Look at my B1s. This should be R omega L, and then I have Vm on this side, and this guy should be minus omega L R, and this guy should be 0. So I now have this matrix for B1, B2, like this. So now all I got to do here is that I just got to go and then I got to solve this thing. Let's see if I'm any better from last time, at least from yesterday here. So let's solve these two. Okay, so let's get the matrix for these guys. So now let's write out the matrix solution. So if I want the solution for B1, look what I'm going to do here. I'm going to take these guys. Remember, this is my B1s, this is my B2s. I'm going to plug this guy in. So this is going to be Bm 0 omega L R. There's my determinant. And then I got to take the determinant of the cofactors. So then this is going to be R minus omega L R. So the first term, look at the second term is 0. So I'm going to get what? R divided by Vm. And then this guy, I'm going to get R squared plus omega squared L squared. Look at that. Right away, you could see that B1, as we start to move towards this direction, B1 is going to be part of the amplitude. Look at that. Can you see that? See how that's frequency dependent? Yeah, that's frequency dependent right there. Now, if I do the same thing for B2, don't let me screw up here, right? So then I got to replace it with the B2. So then I'm going to have this guy here. And so then I'm going to have it for the B2s. This is going to be BM0. But we already know what this guy is. So then you could see here that I'm going to get 0, and then I'm going to get minus minus, which this guy should then give me R squared plus omega squared. And then I'm going to get omega L Vm. And again, look at these little SOBs right here. Look at that. Frequency. And we already saw that the frequency was in the denominator. By forcing it into this way, you're forcing the frequency into the amplitude and the phase. So now that I got B1 and B2, I know how to set up my triangle now, right? So now that we have both B1 and B2, we can compute the amplitude and the phase using the triangle trick. So if I look at my trick here, what I'm seeing here is that, look at my triangle. And what we said here, this is theta, this is B1, this is B2, and then this guy's going to be B1 squared, B2 squared, square root. So I'm not going to write out B1 and B2 again, but let's go do that. So what you're seeing here is that I now can go in here and do this here. So I have B1 squared, B2 squared, then I'm going to have to square these guys. All right, painful. So let's go look at this thing. So I'm going to take the squares of both of them. So look what I'm going to get. I'm going to get, right, this is squared. And this guy's going to be r squared, bm squared. And then I take B2. So I'm going to get the exact same thing in the denominator. And then the top here is going to be omega squared L squared bm squared. And then, of course, I take the square root. So right away, what you can see here is that I'm going to do what? The first thing here is that I'm going to pull this guy out of here. Here, I can pull out, note that I could pull out Vm and I can pull out the denominator. So if I pull them out, I'm going to get r squared plus omega squared L squared. No, I don't think I want to do that. Let me show you why. I just realized the algebra is going to be nicer if you do this. So I pulled out the Vm, but look what I have now. Boy, I'm glad I didn't do that. Look what I'm going to get now. I'm going to get r squared plus omega squared L squared square root. You could see how one of these terms cancels out, right? That term cancels out with that. So now look at our amplitude. It's then going to be, actually, I don't want to write it here. I'm going to write it over here. Our amplitude now is going to look like r squared omega L squared square root times Bm. Wow, that's a big one now. Remember, we knew, right? This is our amplitude. We knew that this was going to happen, right? As soon as we calculated the determinant, we knew that there was going to be a frequency here. So we now know what the amplitude is. So now I can do the same thing for the angle now. So if I do the angle, we know that theta, of course, is the tan inverse of, in this case, B2 over B1. So if I look at this guy carefully here, look at the denominators are the same. If the denominators are the same, it's just the numerators that are going to count. And so you're seeing here that the denominators and the V1s are going to cancel. So the only thing I really have left is R and omega L. And so the ratio here is going to say that it's B2, so it's got to be omega L divided by R. So then I have omega L divided by R. Again, there's my phase. It's frequency independent. This is huge, right? This is huge. Now, in this new language, we get that IL of t, and remember what we wanted to do here. We started with B cosine of omega t, B2 sine of omega t, and we wanted to write this as cosine of omega t minus that phase. And so now look at our solution. Our solution now is now this guy, which will then be the amplitude. And look at the amplitude. It's r squared plus omega squared L squared square root over Vm, and then this guy is going to be cosine of omega t minus theta. Now this is remarkable, because what's remarkable about this here is that this is a respectable solution, right? If I go and I look at this thing here, let me find my mouse so that I can move up. So if I was to make some remarks here about this solution, the first one here is that we started off with a respectable and we mucked it up by now having a solution that has amplitude as a function of frequency and a phase which is a different function of frequency. And somehow that makes sense? Well, it does. Okay, it does. And so if we were to look at the details of this thing, whether we like it or not, the solution for AC steady state has to have an amplitude that's frequency dependent. And so the question is, why? Why is this good? Why do we want to do this here? And what you're seeing here is that, so if I look at the details, so why is this a good thing? Well, if we had really written the solution out, as in chapter 8, whether we like it or not, you're still going to have relationships that look like this, right? You're going to have two ugly terms, right? You're going to have this guy plus this guy. Yeah, whether you want to accept it or not, that doesn't matter whether you want to accept it or not. You still have this solution no matter what you do. But if you do the transition, and the reason why we do the transition is that we want to make a jump to the complex plane easier. We then have an equal solution that reads like what? And in this case, it's going to be cosine of omega t minus theta. And so when I look at this solution, I'm going to get r plus omega L squared. I got a square root divided by Vm. Where theta in this case is the tan inverse of omega L over R. Now, I mean, look at the solution. What would you rather deal with? Would you rather deal with two terms like this? Or would you rather deal with one term like this? I'm going to tell you, I'd rather deal with the green one. It's nicer. It's easier to interpret. And what I mean by it's easier to interpret here is that if there's a frequency change, look where the frequency is at. What I'm saying here is that this solution is much easier to determine frequency changes. Because look at it, right? If you look at the first term, right? Let's box this thing and say this is the red term. And then let's box this one. This is the green term. What you're seeing with the green term, the amplitude only has one frequency dependence. When you're looking at the red term, note that both of those terms have frequency dependence in B1 and B2. So this solution is much easier. So what do I mean by that? So if I look at the inductor current, we can clearly see here that the amplitude of this guy is R squared, omega squared, L squared, square root times Vm. Right? That seems pretty nice. Right? That seems pretty nice. So check this out. I mean, I don't know how much you remember from physics 4B here, but does this make sense here? So if I look at this thing, so let's say that we then plot IL of t versus omega. So if I look at this guy, let's look what this plot looks like. Okay. And as this plot looks like this thing here, what you're seeing here is that this is going to be the amplitude. So this is going to be the amplitude Vm over r squared plus omega squared L squared square root. And then this guy's going to be the frequency here. So remember, this guy is the amplitude. So what you're seeing here is that I'm going to get a max right here. So this is omega equal to 0. So right here, I'm going to get a max point right here. And this max, when omega is equal to 0, you can see that that's going to be Vm over R. And as I go to a higher frequency, look what happens. This guy is dropping. Now, the physical interpretation here is that inductors slash coils have back EMF, right? They have an induced voltage here. So the quicker the current is changed, the larger the back EMF. And this is no surprise here because the way we've written it is that we've written it like this. Or we could take as the limit, right? So this is really my time here. And you could see here is the limit of VL as delta T gets really small, right? Because the time is 1 over the frequency here. And what you're seeing here is that this really becomes sort of like L of di dt. The smaller I make delta t, this gets to a really large value. And so that back EMF, what it's essentially doing here, it's going to kill everything in that circuit. And so at ultra high frequencies, what we say here is that the inductor acts like an open. It acts like an open. So you could see that we can look at the amplitude and go like, wow, that's really, really clean here. On the other hand, what happens if we go and we plot the phase? So this is the phase in terms of frequency versus omega. So if I go and I plot the phase, one of the things that we said here is it looks something like this here. So you could imagine that theta here is going to be the tangent inverse of it's omega L over R. That's what I remember, right? It's gotta be that, right? Just to make sure, because I made enough silly mistakes. Okay, so I got omega L over R. So what you're seeing here, so if you look at the thing here, the tangent, reaches, so if I'm looking at this guy, what am I seeing here? So if I plot this, well, I know that at 0, at theta equal to 0, it's got to be right there. I said that wrong. At omega equal to 0, that tells me that tan inverse of 0 is 0. So if I'm looking at this thing, the maximum that tangent could be is at 90 degrees. So if I look at this guy is telling me that this is when theta is equal to 90 degrees. So that's the maximum they can do. So what you're going to see here is that phase then is going to do what? It's going to climb, and it's going to come all the way to right here. And that's the maximum that it could ever be right there. And yeah, so you can interpret this much easier by looking at it with just one amplitude and one phase. And so that's a good thing here. Now, we can do the exact same thing with the capacitor here. And what I'll do here is that I will probably, I kind of know, I can kind of guess at the solutions. I guess we could derive them. I probably don't want to do that. But I know that the capacitor and the inductor are essentially the opposite of each other, right? So the capacitor and inductors are just the opposite of each other. So we can somewhat guess at the solution. So look what I did here. So if I look at this circuit here, we started with the series circuit and we used KVL. So if I want to make the inductor appear very similar to a capacitor, instead of being in series, we want to make them in parallel, since series and parallel are the opposite of each other. So now let's go look at a parallel circuit here. So what I'm going to imagine here is that now I have a current source. And this current source is going to have some amplitude. And again, we're going to use omega t, just as before. And now, guess what? I have a cap and I have a resistor. And by the way, you should not try what I'm trying to do here. It's just that I have freaking decades and decades and decades of experience. And this is what I would guess here. So if you solve this thing with one amplitude and one phase angles as the arbitrary constant, it's going to look something very, 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 very close to this. So I'm going to go, in fact, I'm going to go grab this solution. Okay. I'm going to go grab the solution because it's going to be very, very similar to this. And by the way, we can Google this if we really wanted to, but I'm going to rely heavy on this solution right here. So then check this out. So what I would expect here is that if I look at the capacitor, it's going to have to look something like this here. So I'm going to write that my VC of t is going to have, so maybe I should write this here. So the amplitude slash phase solution form will most likely look like this. So remember, we can Google this shit. But I would say that VC of t is going to have that B1, B2. Look at the shape of this guy. So the capacitor is the opposite. So it should have the resistor inverted, and then I'm going to have my omega term right in here. So that means I'm expecting that if I get this, it's going to look something like this. It should be 1 over R squared plus, wait. Is that not, no, that can't be right. As the frequency goes, because it's got to be the opposite. So I think it's got to be 1 over omega squared c squared square root I amplitude of cosine omega t minus theta, where theta should be the tan inverse. In this case, it's going to be the reverse, so it's got to be omega c over r. That would be my guess. So look how, just to show you the difference here, look at the opposite effect here. Look at the opposite effect between these guys right here. That's what I mean by the comparison between the two solutions. So then, look what happens here. Look what happens. So look at the plots here. See how this guy gets a maximum at omega looking like this here? That's not the way it is with the capacitor. So if I look at the capacitor thing, so if I now go plot VC of t versus omega, then what am I seeing here? Well, what I would expect to see here is that at omega equal to 0, what I'm seeing here is that the frequency, if I look at this guy, it's got to be the opposite direction then, right? So at omega equal to 0, you can see that the denominator is infinite. So what you're going to see here is that this amplitude should then be the opposite here. And you could see that omega equal to this guy's 0. And so this guy, what you're going to see here is that then very similar to the other one, you would expect here that it's going to sort of like plateau here. So then this guy's going to go like this. At high frequencies, it's going to look something like that, which is surprising. But that's essentially what I would expect in this situation. So enough of that, but that's speculation. And I didn't set up a triangle. All I'm just going is from experience here. But now we're here for the real McCoy here. Okay. And the thing we want now is that there's a reason why I wanted a single amplitude and a phase. Because what takes advantage of this whole thing is the complex exponential. Oh, that's not the way you spell exponential. Exponential approach. Now, I want to be careful here because this is what I want to do here. So what you're seeing here is that there's a progression here. Okay, so our solution, transition, overview, is like this. So we started off with the solution that was B1 cosine omega t plus B2 sine omega t. And what we said here is that when you actually solve this thing for AC steady state, B1 and B2 become frequency dependent. There's nothing we can do about that. And then we said, let's make the solution easier. So what we ended up doing here is that we now went to this solution form where instead of having two amplitudes being frequency dependent, we got one amplitude that's frequency dependent. And what we're going to do next here is that I'm going to show you that there's even an easier way to do this. And the easier way is that we're going to use a complex exponential form here. And what we're going to do here is that when we do this, you're going to see that now we're going to have complex exponential form. And here's how we're going to write it here. We're going to write it as x of m e to the j theta. And it turns out that as soon as you do this, this is the definition of a phasor. And that's where we're heading. So there's going to be a little bit of an intermediate steps from a cosine omega t minus theta to xm e to the j theta. And what we'll do here is that we'll start off with complex exponentials and we'll immediately substitute them into our differential equation. So you could see that these guys naturally appear. And because they naturally appear, we then are going to be able to have better grasp on what is going here. But before I do that, the thing I got to do here is that you got to become an expert at complex analysis. So here we go. Whether you've seen it or not, doesn't matter. This is a review of complex analysis. And it's not that bad. And what you'll see here is that mathematics calls this -1, which we use J because we can't use I because of current. They call this an imaginary number. And you know what? I want to know what dumbass called this thing an imaginary number. A lot of people just say, well, maybe that's fake mathematics. God, that's a bunch of bullshit. Complex numbers are an extremely powerful technique that have enormous applications in physics and engineering. And this is just a gross, nomenclature failure because I can't tell you how many people think that way. It's really is too bad. It is enormously, enormously powerful. And what we're going to find here is that I'm going to try to show you how powerful it is. It's, a big part of this is Fourier analysis. Fourier analysis has its life essentially embedded in the system. And Fourier analysis is the bedrock of the mathematics in Hilbert Space for quantum mechanics, as well as AC analysis for all of electrical engineering. So enough of that BS that I've been talking about. So I need to talk about complex numbers. So complex numbers are either in rectangular, or polar form. What are we most interested in? Is polar form. Why? Because look at the phasor. The phasor is in polar form. Okay? The polar, in fact, what we typically do, you may remember this notation from geometry. Okay? So here we go. So what I'm going to do here is that when I look at this thing here, what we're really doing here is that we want to translate between rectangular and polar form. So here we go. So here are the rectangular properties. And you guys probably know them already, but I'm just going to assume that you don't. And so what we typically do here is that we do the following thing. The first thing that we do is that we go in and we define a complex number C, and we write it as A plus JB. And so what that means here is that if I take the real part of a complex number C, then I'm really taking the real part of A plus JB. And even though I did not state it, I'm kind of assuming that you know this. That's the real part. B is the imaginary part. Okay, so if I take the real part of this, then the only thing I'm concerned with is about the A part. And if I take the imaginary of C, again, I'm only focusing on the imaginary part. And so this is B. Now, we have a very special and important quantity called a complex conjugate. So the complex conjugate is C star. That's how we define it. And all you do is that when you take the complex conjugate, you take the sign of the imaginary part and you make it negative. So then this would be A minus JB. This is an important one. Okay, complex conjugates show up everywhere. Now, what we want to do here is that we need to be able to multiply and divide by complex numbers. So multiplying and dividing by complex numbers follow these rules. So what I'm going to do here is that, damn, I keep going off screen when I'm trying to go up. So the rules are fairly simple here. So if I multiply C star C, then I'm really multiplying A minus JB, A JB plus. And so when you actually do that, you could see that I'm going to get A squared. And then look at that, the cross terms, A plus plus ABJ minus ABJ, that term goes to 0. And look what I get. I get B squared, so I'm going to get J times minus J, B squared, but J times minus J is 1, so then I get A squared plus B squared. You could see how the complex conjugate becomes very important. It tells you the length of a complex vector. Now, if I take the inverse of a vector, a complex number, what we do here is that it's super important that all J values remain in the numerator. Okay, they always have to remain in the numerator. So when I take a complex number like this, all J's must be in the numerator. So what you got to do here is you got to get that numerator out of there. You got to get that j out of there. So the way you do this here is you always multiply by 1. And here we're multiplying by the complex conjugate. So I haven't changed anything. So then check it out. I really have what? C star times C. So what am I going to get in the denominator? I'm going to get a squared plus b squared like we just saw. In the numerator, I'm going to get a minus jb. So I now have that guy in the numerator. Okay, so those are the basics for rectangular. What we want is we want polar form. This is what we're after. So here we go. What we can do here is that when I write polar form, I really mean this here. So I'm going to have C is equal to A plus JB. And remember, this is rectangular. Polar form then looks like RE to the J theta. This is polar form. This is what we want to get it into. And polar form follows the same details here. That means if I want the magnitude, look at the vector in rectangular coordinates, a plus jb. So the magnitude here is then going to be a squared, b squared, square root. And if I want the polar angle, it follows the same rules. It's the tan inverse of the b over a. So that is a very powerful statement of how connected they are with the real numbers here. And so what we want to do here is that one of the most famous relationships in all of mathematics, right? Euler's relation. So I hear that the original headstone of Euler had this relationship on it. So no, that's not true. I lied. When I was in undergraduate, there was a guy in the math department that used to travel the world, and how he chose to travel the world was to take pictures of the headstones of famous mathematicians. So apparently the original Euler headstone only said one word on there. Euler. Dude, you don't gotta put anything more, right? One of the most important mathematicians in the history of this world here. Euler's relationship is that e to the j theta is equal to cosine of theta plus j sine of theta. Dude, this is a badass relationship right here. And by the way, this is quite easy to derive. So if you want to derive this, take the Taylor expansion of e to the j theta. You know what you're going to get? You're going to collect all the cosine terms, which means that you'll get 1. Then you got all the even terms. And then when you get to sine, you're going to see that all of the odd terms have a j in them. So then you get sort of like, theta, then like minus theta cubed, 3 factorial, et cetera, et cetera. Only the odd terms are going to have j, but you get that. So there are 2 extremely important exponentials that should be mesmerized. Okay, you want to mesmerize these. These are outrageously important. There's e to the j times 1/2 pi. So if you plug this in, according to Euler's relationship, you get this. And you could see immediately that, of course, this term here goes to 0. So I get j, of course, sine of 90 degrees is 1. So j is the same here as e to the j times 1/2 pi. This is a huge one. This guy comes up so often. And the last one is e to the j pi. And so when I plug these in, you get cosine of pi plus j sine of pi. And you could see immediately that you're going to get -1. -1 turns out to be very important in phasors. So, I'm going to actually do this as a combination. So I'm going to say, right, very important. And I think this is where I stop off right here. And when we come back, I'm going to go and do, I'm going to start talking about phasor vectors. And as soon as I start talking about phasor vectors, we start doing the phasor calculations. Okay. Oh, I didn't know anybody was here. All right. Thanks for stopping by. I'll see you guys later, man. Appreciate it. Okay, take care.
Thank you, Carlos.